Hello, class. I can't ride the motorcycle until I make the third lecture up, and I can't go outside. And it's actually sort of sunny, although it's cool outside. So I've thrown on my party shirt. I only ever wear this at home. I don't know why I bought it, but I don't really wear it out in public unless I've got a very dark sweater on with it. But today, what we're going to do is really start the beginning of what I would call the course on electromagnetic field theory. Now, true, we've had two lectures already, and that first lecture, you're going to see that first lecture again once we get to, I believe it's chapter 4 in Force on, and we'll talk a lot more about each of the individual equations that make up Maxwell's equations. And I think I pointed out in the first lecture that these are not Maxwell's equations. I mean, they're Ampere's equations, they're Gauss's equations. The only thing that Ampere ever did to it was he added a small attribute to Ampere's equation that would take care of it in a charged plate location rather than just a magnetic field being created by a current carrying wire. So we'll talk about that. We'll talk about a lot of those things, but now we're really at the beginning of this. I may every once in a while, bring up some more things about dimensions and units or conversion factors, just like I used to do in class for those of you who have had me for engineering mechanics. Some of you may not have, though, and so I'm going to cover material that for some of you, just like with dimensions and units, that second lecture, is material that may not be new for you. Maybe if you had me for engineering mechanics, you've gone through vectors like the back of your hand. But there are some people in class whose names I don't remember from the other class, and so I'm going to have to go through a review of basic vector operations so that we can start to get into the higher order differential vector operations like the gradient, the divergence, and so we'll introduce those along the way too. Today what I want to do, though, is I really want to start talking about the forces of nature. And if you don't take good notes here, you should remember what I'm saying, because I'm going to clear some things up for you that most other people who really haven't gotten into elementary particle physics or really don't know, what's going on at the elementary particle physics level, probably are not aware of. So we're going to, be looking at those things too. So where should we begin? Well, I'm going to tell you, we've got 4 primary forces in the universe. And so now I'm going to leave you, or you're going to leave me and my party shirt, and we're going to switch over to the learning pad where you really learn everything, don't you? All right, there we are. And so, like I said, one of the first things that we want to do is we want to look at the forces of nature. So the forces of nature, what do we really have? And I'll describe these. I think everybody knows that we have gravity, right? Gravity is a force. And gravity is a force between 2 masses. So if I have one mass here and I have another mass here, they're not repelled, right? They are only attracted to each other. So we always have attraction. Now, you're probably thinking to yourself, well, what if I had, instead of always having positive mass, what if I had a negative mass? And then you're thinking, well, how could you have a negative mass, right? Well, of course you could have a negative mass, couldn't you? As long as you got a positive mass, we probably can at least envision having a negative mass. I'm not going to go into that, although that is something that we could spend the rest of our lives thinking about as far as gravity and the attraction between the two masses and everything else. We also have our electromagnetic force. And now that's not between two masses, is it? The electromagnetic force would be between two charges. And if I have a plus charge and a plus charge, they repel, right? If I have a minus charge and a minus charge, they repel. If I have a plus charge and a minus charge, they attract, right? Going back to this, you probably say, well, oh my God, the two positive things attract. Do the two negative masses, would they attract too? And probably would. But a negative mass and a positive mass would probably repel each other. Again, all theoretical, thinking about things that are happening at other places in the universe, not in the place that we're at right now. Those two are cues, by the way. I'm using this pen. It's a dark pen. I think I probably should get a better pen. I've been making the studio for the lectures better and better and better all the time. So over the course of this class throughout the summer, I'm sure that everything will continue to get better. So we've got two. So we've got one, that's gravity. And you're probably thinking to yourself, well, I remember back in physics them telling us that since gravity was a constant throughout the entire universe, and now you're probably thinking as you get older, right? And you're more creative, you're more imaginative. You're probably thinking to yourself as you're moving through the system, well, maybe it's not. Maybe gravity isn't constant throughout the entire universe. And we now know that that's true, right? We now know that there are gravimagnetic waves that increase and decrease the effect of gravity throughout the entire universe as the gravimagnetic waves pass through the universe. And in fact, we're finding out now that dark energy is probably just a manifestation of the gravimagnetic waves that are created all the time throughout the universe, which are just causing a rippling effect and then causing the universe to expand due to the ever-increasing gravimagnetic waves. Okay, we're going to talk more about that even in this lecture, but let's finish off Newton's gravitational equation for force. So he said that the force was Newton's gravitational attract constant, and then mass of 1, let's call it mass of Earth, mass of 2, let's call that mass of U, and then that's going to be divided by r squared, r being the distance from one mass to the other mass. So this being the distance r right here, right? The center of mass of the two masses. And so this is what we get. Now you're probably thinking, well, what is Newton's gravitational constant, right? Newton's gravitational constant is 6.67. I'm not saying that you should memorize this. I certainly don't memorize it, but 6.674 times 10 to the 11th. And what we're finding out now, of course, is that it's not a constant. But we're going to use this here. And I'm going to talk about electromagnetic attraction too, in that same vein, in the fact that you were originally taught when you were a freshman that there was a constant called Coulombs constant. when in fact there is no constant, because we know that there is no Coulombs constant, let's say, that it actually is more a manifestation of the dielectric that the electromagnetic waves are working through. Now, the material, in other words. Now, you might say, well, gravity, does that work different due to the material that it's in? In other words, if I was to take 2 shot puts and I was just going to hold them in air, they would have a certain force between those 2 shot puts. But what if I was going to place those inside some type of dielectric or some type of material that's different than air? Would the material change that at all? And I'm sure that what you're saying right now is no, the material should not change the gravitational attraction whatsoever. And it doesn't. I mean, as far as we can tell anyway. But in electromagnetic force of attraction or repulsion, the material that separates the 2 charge has a lot to do with the magnitude of that force. Let that sink in for a second. Let's get back to this though. So, just like I said in the beginning, Newton's gravitational constant, if we wanted to look at the units of this, it would be Newton meters squared over kilogram squared. Now, Newton meters squared over kilogram squared, I think everybody realizes that a Newton is not a primary unit. So the way that we could really write this, if we wanted to write it as a combination of primary units, would be 6.674 times 10 to the minus 11. It's a scientific quantity, so I don't really necessarily have to round it to a multiple of 3, like 10 to the minus 12 rather than 10 to the minus 11. So, and if we actually work that out, the Newton, and then we simplified the fractional combination of primary units, what we would get is meters cubed. I'll let you do this yourself if you want to, but meters cubed over kilogram seconds squared, right? Okay, so that is gravity. Gravity and then the electromagnetic force. I'm going to talk a little bit about this because, you know, we can take this back a little further. What is that force that we've got there? Don't we know with Newton's second law that force equals mass times acceleration, right? And in this case, at the surface of the Earth anyway, let's just talk about the surface of the Earth. This would be m times g, right? M times g. So if I wanted to simplify that a little bit, I could say that g equals Newton's gravitational constant times the mass of the Earth. We're talking about at the surface of the Earth, times the radius of the Earth squared. Now we know that's true, right? We know that g, you know, m is canceled out. The m would just cancel out on both sides, and we just get g. Now we know that g, at least we've been told our whole lives, is g equals 9.807 meters per second squared, right? We know the gravitational constant. So what we could do is we could say that the mass of the Earth is going to be equal to 9.807 meters per second squared. Right, that's the gravitational attraction at the surface of the Earth, divided by Newton's gravitational attraction, 6.674 times 10 to the minus 11 meters cubed over kilograms seconds squared, right? And then if we look back at this, we've also got the radius of the Earth squared. So I'm going to have to multiply that by that too. And now you probably think, well, the radius of the Earth squared, what is the radius of the Earth? The radius of the Earth is around 30, let's say 35, 50 miles, right? So if I have, in fact, you know what I can do is I can just check out what the radius of the Earth is exactly. So let me just do that. All right. Well, it is 6,378.1 kilometers. So let's write that in there. So 6.3781 times 10 to the 6 meters, and I want to square that. All right, and that should give us the mass of the Earth. And you're probably thinking, well, the mass of the Earth, as I remember it, is somewhere around 5 times 10 to the 24 kilograms. And I'm not exactly sure if that is right, but I'm punching it in right now. And I will give you the answer. Oh, I get 5.977. So let's say 5.98 times 10 to the 24. And of course, when we work out the units, that would be kilograms. So 5.98 times 10 to the 24 kilograms is the mass of the Earth. All right. Now, let's keep going. I've got a lot to do today, and we're going to go on to the second one anyway, but let's just see, you know, how all this works. Now, we've got two. I'm actually going to sort of block off gravity for a second, because we're pretty much done with gravity. I think everybody can see how we would use that equation, and I think that people can probably see the parallelism between Newton's formula for the gravitational attraction between two masses, and then, of course, Coulombs' force of attraction. And Coulomb's force of attraction, the way that you probably would have learned it when you were freshmen, is K sub C times Q1 times Q2 divided by the distance between the two charges, right? This being R right there, that distance between those two charges. Actually, I should draw this to the center of the charge, the charge center of gravity, or centroid, as you want to, just like we do that with the masses, right? We look at the center of mass. We're really looking at, between the sun and the Earth, we're really looking at the center of the sun to the center of the Earth, right? We're looking at their centers of gravity, and we would be looking at the centers of charge in these two if there was a charge distribution. We're not going to start talking, we're just starting off talking about point charges. From point charges, we're going to extend into line charges, and you're probably thinking, well, line charge, that would be like a transmission line, wouldn't it? That's right. And then we're also going to talk a little bit about surface charges. And you're probably thinking, well, a surface charge, wouldn't that be what is on one, or really on both of the two plates of a capacitor? right? Because a capacitor really is two surface charges that are separated by a dielectric medium in the middle, right? So when you first learn this K, and you're thinking to yourself, well, K, what the heck is K? I think that we told you originally it was like 9 times. We can actually work out what the units of K are and what they are, because this is not the real equation. And I'm gonna just tell you right now, this is not what grown-up engineers use as their equation. This is what we teach in high school. This is what we teach in freshman, when you're learning about network theory 1 and stuff like that, and really what a charge is. And we don't want to complicate the thing too much. So we give you this equation, and you probably say, but here's the real equation. Let's write that down there. Force, Coulombic force of attraction between two charges is equal to Q1 times Q2 divided by 4 pi epsilon r squared. Now, if we're talking about in outer space, okay, for some reason, I had a little problem there. I don't know what happened, but I lost my internet connection for a second, and I had to redo it. I'm not sure how that's going to affect the lecture that we've got here, but let's just go on. Like I say, I'm getting all the bugs worked out of this system, so it's going to take a little while. And look at this. You see these two equations, and you can see that this really is saying that epsilon. Now I'm going to say epsilon. Now when we talk about epsilon, whenever you see it written all by itself, epsilon is going to equal epsilon sub 0 times epsilon sub r. And you're probably thinking, well, since both of those have the variable epsilon, that they would both have the same units or similar units, right? They don't. They don't whatsoever. Epsilon sub 0 has a value. Epsilon sub 0 equals well, I have no idea what's going on with this thing. I'm going to do another one, but I'm going to have to look at this. For some reason, at a point in time, it seemed like the recording paused itself. In fact, I may not even have been talking most of the time, so I may have to redo this whole thing. Okay. It's a work in progress. Let's just say that.